Our current crop of space telescopes, our upcoming ground telescopes, are amazing, and they're going to push our understanding of the cosmos just farther out into space, give us a better understanding of exoplanets all around us, and yet none of these will be able to give us really good understanding of an Earth-sized world orbiting around a sun-like star. And the problem is brightness, that a star like the sun is about 10 billion times brighter than a planet like the Earth that is orbiting close to you. You've got to block that light from the star so you can reveal that fainter planet beside of it. And there is a lot of amazing technology that's under development to be able to block that light. The general term is it's a coronagraph. And what a coronagraph is doing, and there's a lot of different ways that this works, but you're essentially taking the light that's coming from the star and the planet, you are making the light from the star disappear so that you can just leave the planet. But this is a very complicated technology. The very best that is under development so far that's going to fly on probably the Nancy Grace Roman telescope could reveal a Jupiter-sized planet orbiting around a sun-like star, but we still haven't reached that Earth-sized world orbiting around a sun-like star. And that's going to take a next generation of observatories. Now, my guest today is Nico Deshler. He's a PhD student at the Wine College of Optical Sciences at the University of Arizona. And he is working with a team that just wrote a new paper about a quantum coronagraph. This is a way that you can measure one of the properties of the light itself. Essentially, that light that comes from planets is a little different than light that comes from stars, not just in terms of the wavelength or the polarization, but this other spatial mode. And that you can then filter this light based on these modes. You can dump the light that came from the star and keep the light that came from the planet and be able to resolve it. And they have been able to do tests in the lab that have shown that this technology is going to work. Now, at not the same level of brightness, but in theory, you can scale this up. And so we could see these quantum coronagraphs potentially could be one of the solutions to this problem to allow us to finally see that Earth-sized world orbiting around a sun-like star. All right, enjoy this fascinating conversation with Nico Deshler. Nico, my audience is very familiar with coronagraphs, with the ones that are on the ground, the one that's on the James Webb, and I think have been watching with great interest the various developments. I did an amazing interview with someone from the Roman Space Telescope about how they're going to have a coronagraph that'll sort of test next level technologies. But it really feels like we're sort of reaching this fundamental limit, and it's what we want is these worlds orbiting around sun-like stars. And so you're investigating a different kind of technology, a quantum coronagraph. How is this different from the more traditional coronagraph that people are, mildly familiar with?
Yeah, great question. So I would say there's two parts to this answer. The first is that quantum mechanics gives us a general description of light. So light is a quantum object. It comes in quanta. And you can invoke quantum mechanics for things like exoplanet science in two ways. One, it allows you to calculate what we call fundamental quantum limits to exoplanet discovery. So this is essentially analyzing like the total amount of information that's embedded in the light that you're getting before you make any measurement on it. So what's nice about this quantum analysis is that it doesn't presuppose any type of measurement or any type of imaging architecture or anything like that. This is just what the fundamental limit of the information embedded in the light that you're receiving is. And then the second part to your answer is more on the hardware technology side. So some members in our college here at the Wine College of Optical Sciences, the University of Arizona, they've been looking into, okay, what happens if you leverage quantum technologies on the detection end, and you use some of the sort of funky properties of quantum mechanics to enhance your ability to, say, discover exoplanets or do any kind of astronomical imaging.
Well, so let's break that into two pieces first. I want to go back to the information that is contained within the photons themselves. What information theoretically is available to a person, who is attempting to study the light coming from an exoplanet?
Yeah. So It's also a great question. So there's a lot of degrees of freedom you kind of have when describing light. So I think some that people might be familiar with are wavelength. So if you're analyzing, say, the spectrum of the light coming from um, a planet or a star or something like that, that's what people use to discern whether or not there might be biosignatures um, emanating from a planet. The other degree of freedom you have is actually in what we call the spatial modes that the light excites. So this is a bit more on the physics end of things, but basically there are different, depending on the structure of the scene that you're imaging, um, different patterns of oscillation will sort of appear at your detector, um, and you can process those patterns before actually making a measurement on the light in a way that's optimal. So the light carries information both about, say, the frequency of or the frequency or the wavelength. It also carries spatial information about the objects that are emitting the light, and this spatial information is manifest in the types of like spatial oscillations that you see. Um,
Okay, so I want just to see if I understand this. So you're saying that like you've got two photons that they may have the exact same wavelength, but one was emitted from a star and one was emitted from a planet, and just the size and shape of the object that emitted the photon will influence information, almost like meta information on the photon.
yeah, absolutely. So the technical term that we use for this are called spatial modes. Um, and you can the analogy here that I think is helpful to have in mind uh, as a picture is if you imagine, say, do you play guitar or any instruments, Fraser?
No, I don't. No,
Okay.
no.
Well, if I'm sure you can imagine this still. If you imagine like plucking a string of the guitar, um, there are certain characteristic shapes of the oscillation of the string. So you might have just say one lobe of the string moving up and down. You might have two lobes that kind of oscillate and move up and down
Yeah, I think I'm
alternately.
remembering this from my physics class. Yeah.
Yeah, right. So these are sort of natural modes of the oscillation. Um, and all of that is governed by what we call by wave equations. So light, it's an excitation of an electromagnetic field. So what that means is it's governed also by wave equations. And these modes are certain patterns of oscillations that the light can excite. And which patterns get excited or which ones become more dominant in the signal you receive depend on where the sources of emission are within, say, the field of view of your telescope. So, as you said, like an exoplanet might excite one set of modes, a star might excite another set.
Um, and so then how do you extract this information before you even observe the image?
Yeah. So that's one thing our group was inspired by several other groups before us, excited to sort of explore, was there's a new technology that's sort of coming online now with higher and higher fidelity called a spatial mode sorter. So what this is you can imagine it as a series of phase masks. Um, a phase mask is nothing more than imagine like a piece of glass with a specially designed surface. So the light propagates through these pieces of glass, and what you end up doing is sort of guiding photons that are in different spatial modes to different regions of your detector or different regions of what we call a sorting plane. So you can kind of like siphon out which modes are more excited than others using these spatial mode sorters.
I mean, I think, my audience is probably familiar with like looking at the polarity of the light. And that's another way you can potentially sort the photons as they're coming to you to sort of tease out what is the magnetism of the object that emitted the light and things like that. But this is a different kind of meta information that you can pull out of these photons and sort. Right.
Absolutely. So I think actually between the two of us, we've covered all the degrees of freedom for light. So one is the wavelength, the other is the polarization, as you said, and then the last is the spatial mode. So those three sort of degrees of freedom, that all of that character, like all the information that light could ever carry, is embedded in those degrees of freedom.
Right. And that when a traditional telescope is being used and you're taking a picture, you are capturing the wavelength, in your picture, whatever. And yet when the astronomers are doing these maps of the polarization, they are actually now capturing this additional information. And then there is this third one that is less sort of utilized so far, but this is the new field, is to grab that third type of information that's embedded within the photon.
Absolutely.
Okay.
Yeah.
And tells you about the source, which is
you about the source.
key.
Yeah.
Right. Okay.
Yeah.
All right. I think we got that piece of the puzzle together. So then the second part, which is practically doing this is what's happening in the lab that you're working in.
Yeah. So that's an additional challenge. Like we can write out the theory for all of this. And then there's, of course, building instruments and technologies that actually sort of execute the theory you have in your mind. Yeah, if you'd like, I can speak a little bit to some of the experiments we've done.
Yeah, I mean, I'm guessing that because this is one that is less utilized, it's more complicated, difficult.
Yeah,
wavelengths
sure.
is easy. We have our meat eyeballs, meat cameras, polarization. There's glasses you can put on, but this is sort of next level.
Spatial modes are a little trickier to handle. Yeah, I would say recently the information embedded in spatial modes has garnered a lot of attention in not just the exoplanet community and coronagraphy community, but also in the image science community in general. So people who are trying to do what's called super resolution imaging, so looking at objects that are too small to be resolved by standard telescopes. It turns out that the way you sort of recover the information that is apparent, like ostensibly too hidden in the smallness of the object, is by performing these spatial mode measurements. The way we decided to do this specifically for exoplanet discovery in our lab was by using one of these spatial mode sorters. But we added a little bit of a twist to it. So normally the way these objects work is you have the light, say, from your star planet system coming in. At the output of the mode sorter, you have a bunch of different dots that represent how much light that are basically where the photons for each mode have been siphoned to. So if you were to put a detector there, you would get, there are, say, 1 million photons in mode A, and say 10 billion photons in mode B, or something like this. What we decided to do was, instead of put a detector there, we put a mirror and effectively an occulting mask. So a mirror with a little hole in it. Light from the star, so all the modes that were excited by the star, went through the mirror and off to some beam dump, some place that we discarded the light from. And all the residual light that, say, came from an artificial exoplanet in the lab, back propagated through the mode sorter such that we could make an image. So the idea was, we want to get rid of all the starlight and then, formulate an image, or the best image that we can get of an exoplanet with the star completely nulled. That was kind of our utilization of this.
Yeah, and I think about the challenge with observing exoplanets. Like if there was no star, but yet the planet was being illuminated, then they would be relatively easy to see with our current technology. But it's like 10 billion to 1 the brightness of the star compared to the planet, and so you have to disappear the star to be able to reveal the planet. And if I understand this correctly, what you're saying is that it doesn't matter. You're going to get all the photons from the star. You're going to dump those, but you're going to let through the photons of the planet, and then you're going to use that purely to do an image.
Exactly. Yeah.
Wow. And this works?
So, yeah, I guess. So in theory, it works great, of course.
Yeah, of course, in the lab. Yeah.
In the lab. And then in the lab, it worked decently well. So we recently published a paper with my colleague and friend Itai Ozer, where and he's a magician in the lab. The guy knows way more than I do. But basically where we showed you can, with this technique, get suppression on the order of like 1,000 to 1 just with the mode sorter we used in the lab, which was sort of a proof of concept demonstration. But in principle, with higher fidelity mode sorters, you could drive down this the accessible contrast ratio to or drive up, I should say, the accessible contrast ratio to say closer to what you might hope to find for exo-Earths and things like that, which are, as you mentioned, on the order of 1 billion upwards to 1.
Right. And so what do you sort of envision? Like, imagine that this, I guess you had another 10 years to work on the technology and other people helped out, and you sort of, how would this compare? Because like a coronagraph is this really interesting series of planes where light is coming through and then being sort of bounced around, and then it's interfering with itself, and then it's sort of making its way down into the instruments. And that's if it's just on the telescope itself. And then there's these ideas of star shades where you float this object way out at a distance, and you block the light from the star, and then you combine those together, and that gets you your 10 billion to 1. What would this version, because it sounds like it might be a much more compact machine than a more traditional coronagraph.
Yeah, absolutely. So there's one thing you can almost never get around truly with telescopes, which is the fact that in general, bigger is better. So the larger the diameter of the aperture, the better you'll perform in ideal circumstances, of course. But given the fact that like launching space-based payloads is a really expensive endeavor, and also like manufacturing high-quality chronographs to appropriate tolerance is really difficult too. What we're hoping for this mode sorter-based design is that you can get effectively the same like resolution enhancement that you might get for a large telescope with a coronagraph. But as you said, with this like more compact system, and in principle, there's no reason why you couldn't use that same compact system on any telescope. So the idea is like you have the baseline resolution of the telescope, and then maybe with this technique you can always add like an additional, let's say 10% or whatever, 20%. Just right off the bat.
And so you must have done the math. What is, if you want to make an observation of an exoplanet within a few tens of light years in a reasonable amount of time, how big of a telescope do you think you need?
Yeah. Good question. So I think if I remember right, so we looked specifically at, I think, a 6.7 meter telescope as an example, space-based telescope.
Right. So like just a little bigger than James Webb.
Yeah, just a hair bigger than James Webb. And for different, the amount of observation time you need to say with confidence whether or not there is an exoplanet present or absent around a host star, of course, depends on the relative brightness. So if I'm remembering right, I think if you have something on the order of 1 billion to 1 contrast ratio with that diameter telescope, there are two factors you have to consider. One is the brightness, and also how close the exoplanet is from the star. If it's what we call subdiffraction, if I'm remembering correctly, it's somewhere on the order of almost a day of observation. I could check that to double check. But yeah, we have it in our archive paper if you guys are curious.
Yeah, we'll put a link to the paper. This is the one that I sort of saw on archive, and I'm like, okay, I got to talk to him. I got to talk to, because this is exactly like knowing whether or not there's life on another world, knowing that there are Earth-sized worlds orbiting around sun-like stars. It's like the most profound, fundamental question that humanity has ever asked, I think. And we are now within striking distance of being able to solve this question. Nancy Grace Roman is going to have a coronagraph that will allow it to distinguish Jupiter-sized worlds orbiting around sun-like stars, but it won't be able to find those other Earths. We're going to have to wait for that Habitable Worlds Observatory. But the people on that team feel really confident. And then you've got the people working on the coronagraphs. They feel pretty confident. And the people who are working on the Life Telescope with the nulling interferometer as another, use two spatially separated telescopes to bring together your images of the other world. They feel kind of confident. So, and now you're providing a fourth path to potentially developing this. Does this work well in concert? Like, do these other technologies get better if you layer on a quantum coronagraph on top of it?
Yeah, if you like stack them together, I don't see why that wouldn't be true. The main principle that is like underpinning all of coronography and say the design that we propose is the fact that the information is stored in these like spatial modes of light. So as long as you can process those with high fidelity, no matter what your detection or like collection aperture arrangement is. So say if you had a binary telescope that had two arms that were super far away from each other and you wanted to do some kind of interferometric measurement, however it is that you're collecting the light is up to the engineering limitations. But what you do when all of that light is brought to one place in terms of analyzing the spatial modes, that I think is a general principle you could stack onto any technology. And in some sense, like all the heritage coronagraph architectures that people have made in the past, like starting from the Liotte coronagraph all the way up to more exotic and really fascinating coronagraphs like the vortex coronagraph. There's another one called the Pia coronagraph that use these self-interference effects. All of them are kind of working on similar principles. So they're all trying to siphon out or get rid of the modes excited by a star and preserve while not excessively doing so such that you get rid of exoplanet light. Because those are the photons that are, let's say, most precious. Yeah, that was a long-winded answer to your question.
But yeah. So they would definitely work with those other. Now, we're looking at sort of next generation ground-based telescopes as well. The extremely large telescope comes online in 2027. There's the other classes of these super telescopes. Does this technology work well underneath the atmosphere, or do you really have to go to space?
Oh, yeah, this is a great question. So there's no reason why it wouldn't work well in the atmosphere. In fact, another thing our group has been working on, and this is led by um, a friend and collaborator named his name's Jacob Tarska. He's looking at the use of mode sorters not only for like exoplanet searches and coronagraphy, but also for what we call quantum optimal wavefront sensing. So in a ground-based telescope, you have the atmospheric turbulence, and you need an adaptive optics system to correct for those effects. It turns out that mode sorting also gives you an optimal solution for measuring the wavefront errors. So you could use similar technology, similar platform for both implementing the coronagraph and for doing wavefront measurements.
Wow. So this could help out with an adaptive optics system. Replace it? No.
Yeah. So it would help. So in an AO loop, in an adaptive optics system, you have the wavefront sensor, and that basically feeds back to a deformable mirror, which sort of does like inverts the wavefront, if you want to think of it that way. It sort of compensates for the error in the wavefront. So yeah, it would help adaptive optics systems in that it would make a really precise wavefront measurement device. And one thing that's kind of interesting in that regard is that AO loops, to compensate for the rate at which the atmosphere changes, especially for very large telescopes, they have to be running on the order of like kilohertz. So thousands of times a second, you need to update the shape of this deformable mirror. And what that means is that for very faint objects like exoplanets, you need to extract as much information as you can about the wavefront error per photon that you're receiving, because the scenes that you're getting are so dim. So there's a very constrained, and you're updating so quickly. So the number of photons you're collecting between updates to do wavefront error correction and observation are really small, which means the fewer you have to like direct to the wavefront sensor the more signal you can potentially build up for your like actual imaging system.
Oh, it's really interesting. And so you see this as just being a generally applicable technology to just improving adaptive optics systems here on Earth in all situations, not to mention helping find exoplanets.
Yeah, I think so. I think there's a lot of versatility with this one tool.
Because, for the longest time, I know like with adaptive optics systems, you're kind of limited that you need bright objects in your field of view that you know what their shape is. And then those are used to then make these changes to your telescope mirror itself. And that's why they have these artificial guide stars, because at least you can then put a bright object into the field of view that you know what its shape is supposed to be, you know what it should look like distortion free, and then you adapt based on these artificial stars that you're putting into the field. And so if I understand correctly, you're saying like this gives you some better information about what the underlying source objects are sending your way, that you can then use that as an additional signal to help tune what your mirror is going to look like.
Yeah, that and in addition, I'd say to correct for really high frequency changes or like short temporal changes, short time scale changes of the atmospheric turbulence, you need something that's running at a really fast like update rate. And so under the constraint that you're running really, really fast, you have fewer photons to work with per second to estimate the wavefront. It's another way to phrase it.
Yeah, that's really interesting. Wow. That's very cool. Because I was worried that the atmosphere would pollute the signal if you're trying to make these really sensitive measurements of exoplanets. But this information is constrained all the way through. This mode information is constrained, is protected all the way through the atmosphere of the Earth, and still is delivered to the sensors on the ground.
Yeah, in principle, the information, I would say, isn't lost via propagation through the atmosphere. What's lost is your I think maybe not what's lost, but now you have to estimate a larger multiplicity of variables. You have to estimate the impact that the atmosphere had on the wavefront, as well as say like the position or magnitude of the exoplanet. So doing both of those things jointly is really difficult. But if you have an AO system that kind of can handle one part of that problem, and then you're left with just doing the exoplanet search stuff, I think there's relatively more manageable.
So what comes next? So you've done these experiments in the lab with artificial planets and 1/1000th the brightness. What would it take to then scale up to a bigger version that maybe starts to move this towards a technological readiness that someone like NASA might be interested in?
Yeah. So I think at the heart, because the mode sorter is the heart of this technology, I'd say there are a few pending requirements to get the performance levels necessary for NASA to be like intrigued by such a system. The first is making sure your mode sorters are actually sorting the modes you want with really high precision. So what that means is we have this measure of the mode sorter fidelity, which is called crosstalk. And what this characterizes is how much the photons that are supposed to say be in mode A actually leak into mode B due to like manufacturing imprecisions essentially in the mode sorter. So the more you can drive down this crosstalk and really like purify the modes, the higher contrast levels you can access in principle. So on the manufacturing front, you can try and handle that a few ways. We were using an object called a spatial light modulator, which is like a programmable series of phase masks. But I think a state-of-the-art system would do something like either lithographic printing of the phase masks to get really high precision, or you do maybe like micro machining to get these really, really precise surface profiles. So I'd say that's the main bottleneck, or let's say hurdle that one would have to jump through to see these technologies deployed.
It's funny, like a lot of of advances in astronomy and scientific, NASA development technologies and things have found their way into consumer electronics. When I think about, say, the modern smartphone with its camera system, it is incredibly advanced. The density of the pixels on the CCD on these cameras is ludicrous. Can you figure out a way that this technology that you're thinking about would have, something that Apple would want to use, and then this could sort of drive this technology forward, and then the astronomers could come back around and turn this into their coronagraphs?
Yeah, that's an interesting point. Yeah, I guess like seeing where the commercial industry could push the technology growth and then have it come back to the astronomy community would
Yeah.
be interesting to watch. Yeah, I think
I mean, there's got to be some use in getting that additional information. I don't know how big you could make your quantum coronagraph or on your
yeah.
on your iPhone.
So, uh, huh, good question. I think if there is information, or well, which there is, if there is one use case, it would probably lie somewhere between like enhanced imaging resolution or like compressive measurements. So if you want to say like capture most of the detail in your scene without like storing a lot of data, maybe you can use these mode sorters to uh, uh, yeah, like have a measurement that explains most of what's in front of you without having say millions of pixels.
Yeah. Yeah,
Uh,
like this is tree, that's person, that's a building, and then you can
yeah,
sort of fill in the gaps because the modes that the photons will be coming in at, and then recreate it for huge compression.
in fact, you might find this interesting. There's a group, I think, based out of UCLA, led by Professor Ozkan, that showed you can make what are called diffractive neural networks, which are again a series of phase masks. So the light comes through and gets sort of diffracted through these phase masks, and they basically programmed the phase masks to do object classification. So I think they showed this with like I don't know how familiar you are with machine learning, but they showed this with like the MNIST data set, which is handwritten digits. They showed you can use one of these diffractive networks to like classify handwritten digits. So maybe an application like that could also be
Oh, that's interesting.
found for. Yeah.
Very cool. So, let's say everything goes great. What would be your dream then? Like, would this be flying on the Havre Worlds Observatory? Would this be installed as an additional instrument on the extremely large telescope?
Wow. Yeah. If it managed to get the HWO, that would be out of this world, literally.
Literally, yeah, yeah,
Uh, I think um yeah, if people see that there's sufficient value in such a technology and it has like sufficient robustness to real world errors, yeah, I think it'd be more than a dream to see a technology like this deployed on a real system. The other thing, and to maybe get back to your reference of the word quantum, I just want one thing I should clarify is when we use the word quantum, say in some of the titles for our papers, there's nothing intrinsically, let's say, quantum mechanical about the design of the coronagraph. It's more so we're using the framework of quantum mechanics, so like the mathematics, to assess how much information is in the photons that you're receiving. And then, given that amount of information, we claim and show that there are certain coronagraph designs that can extract all that information and others that don't do that.
yeah. I
Um,
know. I know the word quantum, means whatever people need it to mean, and
yeah,
right.
there's some slop in the word, let's
Yeah,
say.
totally. Yeah,
It's
yeah,
pretty
yeah.
flexible word.
Yeah. Nico, question I always ask people: what are you obsessed with?
Yeah, thank you for asking this question. Let's see. Um, Oh, so many things. Right now, I would say the thing I've been most excited by is actually gearing more towards the theory end of things and less towards the applications. But I hope that eventually it'll reemerge in the form of an application. Um, there's a really beautiful area of quantum estimation theory called information geometry, and it some like abstractly relates quantum states to an, notion of surfaces and curvature in these surfaces. And it turns out that these metrics that we use to quantify information in quantum mechanics are intimately related to curvature and distance in these abstract spaces. So that's one thing I've been really excited about.
So, I mean, is it something that has a practical application, or it's just fascinating mathematically?
I think right now I'd say it's mostly a mathematical intrigue, and it's beautiful mathematics. There are definitely follow-on like application directions I think one could consider. So all of our insofar as the theory of quantum information is predicated on a lot of these information geometry ideas, all applications where we say, oh, we're reaching the fundamental limits of how well, we can perform exoplanet detection or membrane oscillation measurements, how well we can measure up to the fundamental information bounds is based on these more abstract mathematical notions that people have come up with. So I'd say it's more of like an investigation into the analytical tools that we use to assess the quality of our applications.
Right. I mean, like one of the sort of fundamental rules, the laws of particle physics is that there are these very limits of what you can and can't measure, that you can measure, one aspect of a quantum, one aspect of a field, but you can't measure the other aspect. At a certain point, Schrodinger's equations law comes in and starts to put some hard limits on what's possible.
Yeah.
And
totally.
And does this sort of help you explore that latent space?
Absolutely. So the uncertainty limit is something we,
the Heisenberg, the Heisenberg's uncertainty principle,
that's intimately connected to these fundamental limits of estimation theory. And I think given our current understanding of physics and the fact that everything we currently work with the exception of gravity, follows quantum field theory or quantum mechanics. Understanding, let's say, the deeper principles of information on this physical description, I think is both like intellectually enticing, but also has a lot to bear in terms of the technologies we can make and how far we can push. Yeah.
Does it annoy you that gravity doesn't play along?
I don't know. I wouldn't call myself anywhere near as like I don't think I'm nearly qualified enough to even have an opinion on whether or not gravity should be annoying or not. I do think I would say I would actually say no, it's not annoying because it means there's more physics to be understood. So I kind of like the fact that there's an open puzzle.
Oh, that's awesome. That's you sound like the ultimate scientist.
Thank you.
Yeah. Nico, thank you so much for taking the time to chat, and thanks for explaining these concepts. I think it's really exciting, and I know, I'm really looking forward to what you guys cook up in the future. And I can't wait to see this fly in an upcoming space telescope.
Thank you so much, Fraser. Yeah,
right.
It's been a pleasure talking with you, and I've really enjoyed listening to your podcast.
Oh, thanks a lot. I hope you enjoyed that conversation with Nico Deshler. I learned a lot about sort of quantum coronagraphs and sort of what is the state of this industry overall. Now, we had a longer conversation where we talked about a lot of other stuff that he's working on, sort of his understanding of quantum telescopes, as well as how you can use the same kind of technology for other kinds of detectors, potentially using them for dark matter detectors, where you can fire a laser at a detector and then you can take the reflected light and you can sort it based on mode, and that can tell you with high degree of certainty what the laser light is, and so you could use that to make very accurate measurements. So if you're sort of interested in this technology, we've got this longer version of the interview. Of course, that's available over on Patreon. We call it Interview Plus. It's completely free. You don't have to sign up. You can just click the link that's in the show notes right now and just go watch that additional interview. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bieluk, Cy Nelson, David Gilton, David Matz, Dustin Cable, Evan Pearl, Greg Feely, Hans Schultz, Hudson Ward, Jay Graves, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Marcel Smits, Michael Purcell, Modzo, Paul Rohrbach, Ring Kaido, Robeck, Sean Sargent, Stephen Fowler-Munley, Thomas Elskadron, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So obviously, I'm incredibly excited about this technology of coronagraphs. This is the key for us being able to properly resolve an exoplanet. And until this technology has been mastered, until someone has figured out the way to block the light so you get that 1/10 billionth bright exoplanet being clearly visible so you can measure the atmosphere, look at the surface features, understand that world, we're not going to get an answer to that question, are we alone in the universe? And I have done a whole bunch of interviews about coronagraphs, the state of development in coronagraphs. And so I'm going to put a bunch of links down in the show notes. I'll put some here as well. And so you can follow this journey into the current state of developing coronagraphs. All right. I hope you enjoyed this interview. We'll see you next time.